So I think we can start. Some people are still joining, but I guess the first few minutes will be um, known for a few of you. Thank you again for joining this webinar. Today we're going to try to dive a bit more in details on how does metal FFF FDM printing works. We're going to try to give you an understanding of well, the basic stuff. I hope that this will help you understand more and choose the right technology for your application. So I'm going to share my screen. So as I was saying, today we're going to talk about metal FFF technologies and try to give some more in-depth explanation about how does the technology actually works. How does you explain the composition of a filament? How does the post-process works? What are the difference between the different offers on the market? We're going to try to give you some background info on this. Just a few words about Nanoe before we start so that you know where we come from. Nanoe, we're a company focused on producing raw materials for ceramic and also a bit for metal, as you will see, but mainly for ceramics. We make materials for industrial processes and for 3D printing. It's a small company. We're very much focused on innovation and new materials, and you will see that in the next slides. So what our customers do with the material we produce is produce ceramic and metal parts, and they do that with 4 main processes: pressing, casting, injection molding, and 3D printing. Just stressing on this to understand that Nanoe is not a 3D printing company. We're actually a material company with some of our materials going for 3D printing, but some of those going for injection molding, pressing, and so on. And all of these processes, of course, are what we call indirect process, powder metallurgy, which means once you have shaped your material, you still need a sintering to get a bent ceramic or metal part. These materials go in a wide range of application: aerospace, semiconductor, medical, jewelry and watch cases, medical parts, wear parts, really any kind of application where you need high performance material and where you may need ceramic or metal parts. So that's it for the general introduction. I just wanted to give a short brief on these and know about what we do in additive manufacturing. At Nanoe, we've launched a line of ceramic and metal filaments for 3D printing, which is called Zetamix, and I'm going to explain a little bit about that before going to the topic of today. So what we do at Nanoe, again, in that field, is we make raw materials for 3D printing. We make filaments that are compatible with FDM printers. This comes from ceramic and metal injection molding compounds that are extruded into highly loaded filaments of alumina, zirconia, and stainless steel and H13 steel. We mainly offer the material, that means ceramic and metal filaments, but we also do offer compatible printer, debinding, and sintering furnaces to use our material. This is something really crucial with that kind of technologies. You really need to have a compatible equipment that has been co-developed or at least adapted to the filaments you are going to use. And this is what we offer also. We offer sintering furnaces, debinding kits, and printers. How does the process work? We're going to go back on this when I'm going to talk a bit about metal FDM, so I'm not going to go in much detail, but basically it's a 3 or 4 step process depending on materials. For ceramic, we have a 3-step process: printing, debinding, and sintering. Debinding, which is done chemically. We dip the part into a solvent. In the case of metal, it's a bit different. We have removed the chemical debinding, so we only have printing and sintering, which is done directly in our furnace for H13. And the last one is 316L. It's a bit more complex because it usually requires hydrogen atmosphere, which is a bit more difficult to obtain, which makes it more compatible with industrial furnaces. So that's the main materials we offer at Nanowee. What we do like about this technology and about our offer in that field is that this is really probably the easiest way to print ceramic and metal on the market. You don't have any other technology that would be more simple to use. You'll see that it's more complex than it actually looks like, and I'm going to dive a bit into that afterwards, but still a very easy to use system and a really low cost investment. That's the two main points. It's affordable and it's easy to use. When we say affordable at Nanowee, we offer a system that starts at 10,000 euros, and you really have no equivalent on the market where you can print ceramic and metal parts for that kind of price. Of course, it's also a very versatile technology because you can print a lot of different materials with relatively good accuracies, at least compared to what you would expect. So that's it for the presentation of the company and what we do in that field. Let us go a bit more in detail about what is exactly metal FFF technology, FFF FDM, metal filament deposition technologies. How does that work? What's inside it? The first thing is you've probably heard a few times on the market talks about what we call MIM-like technology. This is considered to be a MIM-like technology. MIM meaning metal injection molding. So this is a technology which is clearly derived from metal injection molding. So let's understand what we're talking about. This is the process cycle of metal injection molding. Basically, the principle is quite simple. You mix a powder, a metal powder with a binder. You inject it in a mold. This injected part is afterwards debinded. That means we remove the binder and sintered to get to a dense metal part. The principle with FDM is exactly the same, except we replace that step of injection molding by FFF FDM printing. This is what we can see here. The main process being compounding, so mixing of powder and binders, extrusion, of course, to get a filament out of it, printing, debinding, sintering, and you get a final part. The debinding part might be optional. In some cases, we only do thermal debinding, which means you have one step less, but still always the same principle. You mix a binder and a powder, you print it, then you remove the binder, and you put it in a furnace to get a dense metal. Always really a quite straightforward process. So let's look into these several steps in details. The first step is compounding and extrusion. That's probably actually the most important step. That's what's going to give you the quality of the material. Here are a few keys to understand what's inside a filament and what makes it good or bad. The first thing is if we zoom a bit on what's inside, in a spool of filament, you'll find, of course, some powder and usually a combination of at least two binders, sometimes more, a primary binder and a backbone, sometimes they're called, which will give different properties to the filament, some flexibility, some hardness. One of them might be soluble. So it's usually a combination of a few different binders. A lot of additives also, and of course, a lot of powder. And that's really the crucial point. There's this question of how much powder you have inside a material. When you're developing a filament, there's really usually a dilemma between you want basically a filament that's as easy to print as possible. So that means flexible, non-brittle, with reasonable printing temperature, all of these things. But on the other side, you also want to have a very high loading of metal or ceramic powder. If you don't have enough powder in your material, it won't be possible to get to a dense material afterwards. And usually what we say is we need around 50 volume% of the mix that should be metal powder. That's something really a critical point here. We're talking about 50 volume%. That's a very high amount, and usually people don't really see that. I'm going to explain a bit of detail. I'm talking in volume and not in mass. And you should be careful about one thing, which is, of course, binders are usually with relatively low densities compared to metal, and that's going to have a huge influence on the actual mix. We say 50 volume%, and that's really a very high amount if you convert it into mass. To give you an example, here are two filaments that you could find on the market. If we talk in mass, one of them has 89% of metal and the other one has 80. You could say, well, the difference is not so much. It's very close, 80 to 89. That seems similar. If you calculate it in volume% with the density of the metal, which is 8 times bigger than the binder, you will find out that actually this is a huge difference. In one case, you have a target, which is 50 volume%, and in the other case, you have only 33%, which might look great, but will not be enough to get a dense metal part at the end. This is also true for ceramics, by the way. This is one of the most important aspects of a filament formulation is the amount of powder that is present inside it. And well, a simple way to ensure it is usually filament manufacturers should talk in volume. If they talk in mass, if they say I have 80 or 70 or 90% in mass, you should be careful because that may be hiding something. The logic should be to talk in volume and to aim for 50 volume%. That's really a very important thing, and that's what will allow us to get to a dense part at the end. And we're going to see that afterwards. So that's it for the formulation. The really important thing here will be to see how much powder you have and what's the rest of the binder, each of the elements bringing something specific to the filament. So once we have a filament, we print it. That is usually quite straightforward. So I haven't put a lot of information here. It usually looks a lot like FFF printing with thermoplastic, except that the filament is quite brittle, but still relatively similar. And once you have printed it, you get to the crucial part, which is debinding. This is usually where you will see the big differences between filaments. Some filaments are relatively easy to debind and some are much more complex. And this is where you will see if the filament is good for making metal parts or not. There's usually 3 options on the market, which are quite well known. The first one, the most basic one, is thermal debinding. And then you can also do chemical debinding and catalytic debinding. I'm going to precise a bit these options and what they mean in terms of pros and cons. So the first one is thermal debinding. How does that work? It's quite simple. You just put the part in the furnace and you heat up very slowly to burn the binder away without losing your shape. And that's not that easy to do without deforming the part. This is what we do at Nanui, of course, for our metal material. It's also what Desktop Metal is doing with their new version of the studio system, but this is probably the only 2 players who are actually doing thermal debinding for the moment. In some cases, you will have some deformation of parts, and a few suppliers may suggest to use a powder bed to keep the shape in place. This for us has a few drawbacks, so when we can, we should avoid it. So what are the pros and cons of this way of doing things, this technology? The obvious advantage is you remove one step from the process. Instead of having printing, debinding and sintering, you actually have printing and heat treatment, which will do both debinding and sintering. So this is really a way to make the process more simple in terms of number of steps and also in terms of equipment. So this is why we chose to go in that direction. Of course, that means you don't need, there's no hazard associated with solvents or acids or whatever. So that's also a big advantage for this way of doing things. What are the cons? Why don't everybody do that? Well, the first thing, which is very obvious, is that you have quite a big risk of having deformation during thermal debinding. So the way we remove the binder is by hitting the part progressively so that the binder is going to be thermally decomposed. But of course, you're going to be at some point at a temperature where the material is relatively soft. This is how you printed material. So of course, it is soft around 200 degrees Celsius. And so you need to find the right thermal cycle that the part will get hard and have decomposed sufficiently before it is too soft. And that's really a very tricky thing to do. So that does pose some difficulty. It's a bit more complex to implement. The other thing that goes with that, it's a relatively slow process. That's quite logical. If you want to avoid this deformation, you'll have to go relatively so slowly during debinding. The rest is also about the chemistry of the material. You will have to choose between debinding under air or under neutral gas, and both of them have some problematics. If you do it under air, you risk oxidizing the material during this thermal process, and if you do it under neutral gas, you have the risk of leaving some carbon in the material, which would not be good for the final material. So that's really a very fine compromise you need to find. It's not that simple to find the right process, and it certainly takes some time to find the very precise temperature settings and curves so that this can work. So the other way, if you don't do thermal debinding, is to do chemical debinding. What happens when you do chemical debinding? So I'm sure you remind, I told you there is quite often two binders in the filament. Well, what you're going to do is you're going to soak the green part in a chemical bath, typically in acetone or other solvents, and this solvent is going to remove one of the two binders. It removes what we call the primary binder and leaves the backbone, and the backbone is later on thermally debinded. So when you put it in the furnace, you're going to burn it off. This is typically what Markforged and Desktop Metal are doing. And really, you should note that you still do have a thermal debinding. So you have a chemical debinding and then a thermal debinding. But it certainly makes the thermal debinding more simple. So what are the pros? It's a faster process because you remove part of the binder before going in the furnace. It removes a bit the risk of deformation during thermal debinding, because once you have done the chemical debinding, there's not enough binder left so that the material could be soft. And that means you can ramp up a bit faster because you don't have that risk of deformation. And it also removes parts of the carbon, so that removes that problem of carbon contamination in the metal. On the cons, of course, you have the chemical handling. You handle solvents, which means you certainly need to be careful about health and security. You may need to invest into dedicated equipments. And also the chemical debinding can leave some strain in the material, and sometimes it can cause some cracks in the material. So that's, of course, a very efficient way of making parts, but still it has also some cons. The last version is catalytic debinding. So it's basically the technology of one company, which is BASF. How does it work? So the parts after printing are placed into, let's say, a specific and adapted furnace where you can inject nitric acid in a gaseous form at a few hundred degrees Celsius. And these gases will catalyze the transformation of the binder into another gas and some remaining backbone again. Usually the binder that is used for that is POM, and it will be transformed into PP plus formaldehyde. And then again, the backbone will be removed later on by thermal debinding. But again, there's a lot less binder, so it makes the secondary step, the thermal debinding, more simple. What are the pros and cons again? It's probably the fastest process on the market for debinding. POM does make very strong filaments, so they're probably going to be the less brittle filaments on the market also. They're really very strong. It again removes the risk of deformation, and it removes part of the carbon contamination. That's a good point. On the cons, it's quite a high capital expenditure. The catalytic debinding furnace itself is usually industrial equipment. So you can find some lab equipments, but it's still usually quite expensive, which makes it either a significant investment, or there's always a possibility to outsource debinding and sintering, which is quite often done in this case. And the last step, which is really crucial, of course, is sintering. What happens to the part that has been debinded, what we call the brown part. The first thing you need to understand, it may seem obvious for a lot of you, but some people keep asking, so I would rather say it quite clearly. Sintering is very different from actually melting, from casting a metal. It's completely different. We're not melting the metal, we're sintering it, and that's a complete different way of doing metals. What happens during sintering is, well, basically you'll have three stages. The first one is the thermal debinding. We talked about it already. Then between 800 degrees Celsius and 1000, 1200, you're going to start having some connections between the grains, which will make the part solid. It will give some strength to the part. It's not yet a dense metal, but it's relatively strong. And if you heat up more, you're going to get to a temperature where you are not melting the metal, but still the metal is at a temperature where it will start move in a solid phase. What we call solid diffusion will happen. The grains are going to get bigger by, let's say, condensing together, agglomerating together, and there you will get a dense material. It's quite important to see that these stages are present because in some cases, a few offerings on the market will actually stop at the neck formation. So they will make very porous metal. It is always an option, and it may work for some application, but of course, the mechanical strength is going to be much lower than if you actually get to the dense solidification of the part, which usually happens in the range of 1200 to 1400. The one thing which goes with that is if you have some densification without melting, the material needs to come from somewhere, and what happens is the part will shrink. And that's really one of the major problem with MIM-like technologies. If you sinter a part, you have shrinkage, and shrinkage is going to pose a few problems. The first one is obviously you'll have some risk of deformation and cracks. Secondly, you will get to dense metals, but not fully dense. It's very difficult by a sintering method to get to more than 95% density. You will need some support for sintering. That's also one of the problem with this, especially for metals. For ceramic, it might be a bit different, but for metals, you will definitely need support for sintering. And you can't make huge parts. It's not a technology which is made for big parts. It's made for small and medium parts. If we dive in more details, the shrinkage will cause some other problems. The first one is it will limit precisions to plus minus 0.1 on a small to medium part, maximum 10 centimeters. And when I say plus minus 0.1, that's already for someone who really has a good experience of the technology. For some complex parts, it may be more. It is really a limitation to the actual precision of the finished part. If you need more precision than that, that will need some post-machining, almost certainly. The second thing is usually shrinkage is not isotropic. So X, Y, and Z are usually different. You may say, okay, that's acceptable. We just have to have the shrinkage factor for X and Y and the shrinkage factor for Z, which is definitely something we would agree with. The other problem, and that's really more problematic, is that shrinkage may vary a bit with geometries. So you won't have the same shrinkage for, say, a pyramid, a cube, or a cylinder. And that, of course, is a problem because you would ideally want to have exactly the tolerances you were aiming for on the first shot. And sometimes it's not possible. If you are really printing something complex, and complex may not be what you think about. Complex may be not the shape itself, but varying thicknesses or the size of the part may make it difficult to have a good part on the first shot. If you need tight tolerances, you may need some trial and errors before you actually get the right part. And of course, that is a drawback of the technology. All of this depends on your tolerances. Are you on very tight tolerances or not? But depending on that, sometimes you will need trial and error. Let's talk a bit about sintering atmosphere. When we sinter metal, we need furnaces that will be put under neutral gas, protected atmosphere, for a very simple, understandable reason. If you sinter it under air, very quickly, the metal is going to oxidize. And instead of having a metal powder, you're going to have an oxide powder, and you won't be able to sinter anymore. So there's three options usually on the market: sintering under neutral gas, sintering under argon plus a bit of hydrogen, or sintering with pure hydrogen. And this will really depend on the material you're sintering. Some metals are very non-sensitive to oxidation, and you can sinter them under any neutral gas atmosphere. Some metals are a bit sensitive to oxidation, and we will prefer to sinter them with a bit of hydrogen, but in some cases we may even need pure hydrogen, and that's really the more problematic thing. Why is it problematic in that case? It's for, again, a quite simple reason. If you get to more than 3% of hydrogen, the gas mix is explosive. Less than 3%, it's considered non-explosive, so there's really no specific hazard. You can actually buy the pre-mixed gas, which allows you to avoid completely any inflammable or explosive gas. But if you need more than 3%, well, you will need a very specific set of equipment. Of course, hydrogen is also quite expensive. To give you an example of the kind of equipment we're talking about, on the left, you have the kind of furnace we offer, which are compatible with neutral gas or argon plus 3% of hydrogen. If we needed more than 3%, we would need to go to more industrial furnaces with a lot of, I would say, specific security equipment to avoid any risk during the manipulation of hydrogen. So that really changes a bit the logic. In one case, you still have something which is relatively desktop, and on the other case, you have something which is really more industrial. And this basically depends on the metal you want to make. The reason we do like a lot tool steel is because it's a lot easier to sinter. It can be sintered at the neutral gas, or even ideally neutral gas with a little bit of hydrogen, which will make it more reliable. Whereas all of the other metals that are listed here would rather be recommended for hydrogen. So you can sinter a few of them under a mix of argon and hydrogen, but it's the ideal conditions where you would get the best densities is pure hydrogen. Of course, you also have ceramics where you don't need any neutral gas. That's something different. They're listed here, but they're no metals, so that's a bit different. So what's the takeaway from this short presentation? The first thing is really, you should choose the process which is adapted to your application. We presented you a few options here. At Nanoe, we offer one specific set of filaments with an adapted furnace, but it may not answer to your needs. It depends what you want to do. The question here will be, do you need to print medium or large quantities? Do you want to have the post-process internally or not? Can you have the right environment for that kind of furnaces? If you wanted to have it in-house, you will need some neutral gas, you will need some ventilation, that kind of stuff. So this is really something that should be looked at the beginning of the project so that you choose the right material. In some cases, you may want to outsource the post-process, and clearly there are some solutions on the market. In some cases, you may want to internalize it. So that really depends a lot on what you want to do. The second takeaway for us is that there is a very fine tuning between the raw materials and the post-process. If you want to have a right material, you need the filament and the post-process, which is why we decided at Nanoe to offer the furnaces so that we can exactly offer the same post-process we have at Nanoe. We can offer exactly the same to our customer. And finally, well, I'm sure you've understood it, but metal FDM is far more demanding than plastic FFF. It does require some learning curve because you have some chemistry, especially for those who make the filaments, some powder metallurgy, some material science, some 3D printing skills, all of this put together. So it looks simple on the principle, but it's actually a bit more complex than what it looks like. So diving into that technology does require to put a bit of time in it. So this is for industries or for laboratories who really will have some uses of these materials on a regular basis. I don't think it makes sense to start printing metal by FFF if you just want one or two parts. If this is what you're looking for, you should probably outsource the full process, including the printing. And I think you should look into getting there, investing some time and potentially some money into the furnace if you want to have the post-process. You should look into this if you know that you will have some recurring requirement for metal parts, because it will still need some learning curve. You're not going to have the perfect part on the first day. You will print some parts, they may be quite good, but before you really have the best properties possible, you will need to learn a bit about the technology. So that's really our advice at Nanoe. You should look at your application, look at the number of parts you're going to need, and depending on that, you may choose to dive in and to learn about printing metal with that technology, or you may choose to outsource, and in some cases that may make more sense. Well, that's it for this short presentation on metal FDM FFF printing. I hope this was clear, and of course I'm completely open to questions. So if you have any, you can put your questions on the Q&A section, and I'll try to answer them now. So some questions. The first question was, how are supports designed for FDM metal and the process chain? That does depend on the offerings. So in the case of Nanoe, well, we use standard FDM printers. We don't manufacture a specific printer, so we use printers from the market, and we also use the slicer from the market. This clearly has some significant advantage in terms of cost, but that also means that we use the supports that are designed for typical, clear, simple FDM printing. That does work relatively well, but our supports are designed in the slicer, just like some usual FDM supports. So sintering in vacuum, yes, that's done sometime. It's an alternative to hydrogen, or sometimes you will have a partial pressure of hydrogen. It does have a similar effect, so that it will remove some of the oxide layer, which is on the top of the powder, and it will help the densification of the material. Have you tried to print with dual extruder ceramic and metal filaments in the same print with razors or other printers? The desktop metal approach. So we have made some trials. For the moment, let's say it's not an option we're offering. The ceramic filaments we develop are really made to print dense ceramics. They're not made to print supports. They're really here for the dense ceramics. So how thin can be printed walls? So that really depends on what you call a wall. Is it an unsupported wall? Is it supported? So that's a bit complex to answer. The thinnest wall you can print is going to be the size of your nozzle, 0.4 millimeters. But of course, this wall during debinding, and especially during sintering, you will get to a temperature where you are very close to the melting temperature. So the metal is relatively soft. If you're not careful, this nicely printed, very thin wall may break or may sag during sintering. So that's depend a bit if it's an unsupported wall, but we usually give a height to width ratio, and probably we'll do another webinar about metal design guide. That's certainly worth it. Because that's included in our design guide. So how are behaving the stainless filament in vacuum thermal debind and sinter? So the first thing is usually we don't do a complete vacuum thermal debinding because in those temperatures you do need some partial pressure. So usually we do use a bit of argon at least for the debinding part, and then you could go to a secondary vacuum for the sintering. Well, it behaves relatively well from what our customers tell us. At Nanoe, we offer a system where we don't do vacuum sintering. We do sintering under neutral gas, but we don't do the vacuum sintering. But from the experience of our customers, this does yield some good results. And an experience in porous materials, well, there's two different answers here. The first one is, of course, one of the interests of FDM is that it can print porosity. If you need big porosities, you can print infills, and that's usually very favorable. We do that a lot. But you could also choose to leave some porosity in the material by sintering at lower temperature than the actual densification temperature. That does work, but may have relatively unpredictable results. Is it possible to mill the green parts to have better surface and tolerances before sintering? So the answer to that question is yes, it's possible. We do a lot of this for improving the surface roughness. It may help a bit with tolerances, but you can't expect any miracles here because the most problematic part in the tolerances comes from the sintering and from the shrinkage, which means even if you have something which is perfectly precise before sintering, you'll still have sintering and you may have some deformation there. It seems there's a high potential for the risk of porosity inside the final component. How can the final component be controlled from the porosity point of view? That's an interesting question, especially since in a lot of cases, we're not going to print dense part. We're going to use the FDM capability so that we're going to print parts with infill inside. So we actually print some porosity inside the material. So you can't control the density in a traditional way. The traditional way would be to just measure it by Archimedes measurement, but that won't work here for the reason I say, because we actually print some porosity inside. So how do you control it? There's a few things possible here. A lot of the work is still done with some destructive testing. You can also print some benches, some small part that you will put in the furnace to check that the densification goes well. You can also control a few things, especially the mass loss and the shrinkage will give you a very strong indication on the level of densification you have achieved. If you don't have the right shrinkage, that means you haven't densified your part. Can we really proceed to the metal FDM widely as polymer, or still need more technicity and people with skills? Well, it's not as simple as printing PLA, if that's the question. You will need some people who can understand a bit the process, and I would say especially you need people who will spend some time to learn the technology. There is a learning curve, which is a bit longer than with PLA printing, but you do have a learning curve when you start 3D printing also. I would say that's similar. But yes, you need people who understand a bit and who have time to learn by themselves. So we do give a lot of help, some design guide, some recommendation on printing and so on. Our competitors also, of course, at least let's say the serious competitors. But even with all of this help, there's still some learning to be done by the customer himself. What is the size limit for metal FFF? So there's no final limit to that. There's no absolute value, but we usually recommend to stay in, let's say, a box of 10 centimeter wide, 10 per 10 per 10. More than that is more challenging. It's not impossible, but it's a lot more challenging. What nozzle size do we recommend? I think we use a lot of 0.6 millimeter, but we also print it with 0.2 millimeter. It really depends, but 0.6 is, I would say, a good value. So how does the 50 to 55 volume percent compare with MIM feedstock? It's similar, somewhat slightly lower, but in the same region than MIM, and that's really where you need to be. If you don't have that minimum of 50 volume percent, you will probably have some problems. But with MIM, sometimes you can go a bit higher because the pressure you can apply in an injection molding machine is higher than what you can apply in an FDM machine, but still in the same region. Do you have customer projects connected with creating porous wicks for loop heat pipe application? I'm not sure I understand completely the question. I would be happy to discuss that later on a one-to-one because that does seem a bit specific. We do have a lot of application regarding heat, both with metal and with ceramics, either for heat-resistant material or for heat conductors, so that we can make heat evacuation out of parts. But for this one specifically, I guess that would require some one-to-one conversation to know more about it. I can see there's some more question here. Thermal decomposition of binder usually release some harmful gas. How this concern is managed? So that's a good point. I would say that's something that you'll have to deal with. Whatever the process, you will have some, well, you're basically decomposing some plastics in a furnace, which is, of course, something you should be careful about. It does depend a bit on quantities. With reasonable quantities, with desktop solution, you can just live with having the proper ventilation system. So you will just take away the fumes, and you really need to have a ventilation system with an outlet. It's not just recycling the air and filtering it, it's evacuating the fumes. Is there a density difference between the part printing with a nano solution and the part printing with equipment from DM and Markforged? So to be perfectly honest, we haven't completely benchmarked. So we don't have parts from DM and Markforged. From the data sheets, I would say it's similar. clearly the big advantage of closed system is that it's an integrated solution. So the material, the machine, the software, everything is developed by the same company. So it's a bit more plug and play. And that's an advantage they will certainly have. They also have a more diverse portfolio of materials. They offer more different metals, but they don't offer ceramic, which is something we do. I would say that, again, that really depends on your project, but it's not really a question of material density. I think here we are probably comparable. I see some people have answered to the questions before I got there. What about the surface? Is it rough after sintering? Well, it really looks like the printed surface, nothing more, nothing less. The surface is very similar. The good point is once you have sintered the part is really very strong, and you can use any usual post-process method you would use for metal parts. So tumbling, sandblasting, whatever you are used to, you can use it for those parts. I've seen some questions about ventilation here. So yeah, again, ventilation is the way for such technology. Clearly, if you go to higher volumes, typically in the MIM industry, there is some post-treatment of the gas, but we don't have the same volume, so the ventilation is sufficiently a sufficient solution, and it does respect regulations, if that's the question. So I see that some people have been answering to the question in my stead. That's great. Alors, une question en français. La rugosité est une problématique pour les pièces sorties de fabrication additive. So some other question about surface roughness, and does the surface roughness have some impact on the mechanical strength? So the answer is probably yes. Usually we do mechanical strength on a polished surface. So we remove that specific aspect out of the equation because we want to know the material properties of the bulk. But it is likely that the surface roughness will impact negatively the mechanical strength. And a question about the surface roughness again and the materials is different with alumina and zirconia. It is a bit different, but still similar. The surface roughness comes from the process more than the material. So we will have the similar surface roughness, which is basically linked to the fact that we're printing layer by layer. You print layers of 100 micron, which means in the end you have the surface roughness linked to these lines of 100 micron. Some materials are easier to smooth out afterwards than others. It works really very well with zirconia, for instance, because zirconia is a great material for polishing afterwards. So the post-processing techniques used for metal FFF parts, can we use the same methods like metal grinding, tumbling? The answer is yes. That's one of the good points. You can, if you need, for instance, one very tight tolerance in one place on your part, this is clearly an option to print it and then just to sinter it and then to post-machine this one specific place where you need the tight tolerance. That's something which is quite often done, and that's one of the big advantages of metal, which means they are very simple to machine if you compare it with ceramics. So there's a question on metal. We actually don't do any aluminum filaments yet. That's something, there's been a lot of talk in additive manufacturing about 3D printing of aluminum material by a sinter-based method, but we're not there yet. This is something quite complex, and I guess not yet ready for industrialization. The difficulty with aluminum being this layer of oxide we were talking about on the powder is really very strong on aluminum. Well, that's it. If you don't have any more questions, we can close the webinar for today. Of course, we will be doing some more webinars in the future about metal printing, about ceramic printing also, some webinars about applications. I think that's also important. So you should keep posted. You should follow us on LinkedIn so that you know about the next ones. Thank you again for attending, and hope to see you at the next webinar.